Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. And today we have the paper Dynamic Neural Radiance Fields for Monocular 4D Facial Avatar Reconstruction. And we have the first author, Guy Gafni, here with me. Hello, Guy, and welcome to the podcast.
Hi, I'm very happy to be here.
Okay, so for the new listeners, every episode of the podcast is constructed kind of like a paper. So the first part of the paper is the authors. So, Guy, please introduce yourself.
Thanks, Itzik. So my name is Guy Gafni. I'm a PhD student at the Technical University of Munich. And today I'll be talking about the paper that Itzik presented. I will not repeat the title because it's just too long. But basically, we do 4D avatars with NerF. This paper was written with my collaborators Justus Thies. He's a postdoc at our group. Michael Zollhöfer, who's a researcher at Facebook Reality Labs, and Professor Matthias Nießner, who's my PhD advisor.
All right, and this work was done as part of your PhD.
Yeah, this is my first paper in my PhD.
Cool. Okay, so let's dive into the abstract, or in our case, the TLDR. So, in 2-3 sentences, So, what is this paper about?
This paper is about rendering portrait videos from novel head poses as well as novel expressions that we can control. So you can think of it as talking heads, basically, that you control which pose the head has, or conversely, basically, where you're seeing the head from and what expressions the person is having at the moment. So, yeah, this can be used for kind of reenactment, whereas most papers out there just do reenactment of the face. Here you also gain control of the head pose, which makes it kind of special.
So, for those that are not familiar with the field, so when you say reenactment, what do you mean?
So reenactment means changing the facial expressions of the person. So if you have one person saying some sentence and then you want it to seem like the other person is saying the same sentence, you have to change his facial expressions to match it. So it relates to deepfakes, which is a very general term, which I don't really like using, um, where it seems like Obama or Trump are saying something that they didn't really say because you have an actor in the side who's saying this, and you're just transferring the expressions.
Okay, so we kind of dived into the introduction already. So, what is the problem that this paper is addressing? So, why is this an important problem?
So if you think of the good uses of facial reenactment or novel use synthesis of humans, it goes to VR applications. So right now, you and I are having a video chat, which is simply 2D. And now, if I move to the side a little bit, ideally in a real world, I would be seeing more of your ears now. So I would be seeing one side of your face exactly. But that doesn't happen right now. If I move, I still see the same picture on the screen. So I would like to control your head pose as I move. So imagine you are now wearing VR glasses or a VR headset. So as you move, you want to see different parts of me. So the software that has to render me has to change my pose, right? And that's why we want to do the novel head pose synthesis or novel viewpoint synthesis. And the expressions is, so if you want to re-render a video from a different viewpoint, you still have to kind of replay the same expressions
Mm-hmm.
that the speaker had. But it's also cool to be able to change the expressions. For example, for dubbing, if you now want to dub this video into a different language, then there will always be a mismatch in the lip sync. So you could have an actor who's speaking Chinese right now, and then you transfer his expressions onto me, and it would seem more plausible that I'm actually speaking Chinese.
So these are very interesting applications that can fit into our day-to-day lives. And so, what are the major challenges here?
Um, the major challenge is photorealism, right? As soon as you start editing the face, you just get artifacts with all these generative methods.
You want to do something that's very photorealistic, and if it's not photorealistic enough, it just looks odd. Okay, so what's the main contribution of this paper?
So the main contribution actually goes back to NERF. For those of you who don't know, NERF was a paper from ECCV 2020, which made a huge impact on the novel viewpoint synthesis community. What they do, they take a volumetric approach for a novel view synthesis of scenes. So basically, you have a bunch of images captured from different camera poses in a scene. You assume you know these poses. You can get that with like structure for motion software. And what they do is they pose these constraints over shooting rays from each camera viewpoint into the image plane. And they sample points along the rays. And they have an MLP that predicts RGB values and density values for every point on the ray. So they're able to then take that and they do volumetric rendering along the ray to get the final color value of the ray and compare that to the color of the pixel. And what this does in the end, it gives you a continuous representation of the scene by an MLP that at every point in space, every XYZ in space and viewing direction can give you the color value and density of the scene at that point. So that worked really well, kind of rattled the whole community, and there were so many NERF papers that came out now. And these NERF papers usually assume
NERF explosion.
Exactly. Whoever is interested in it, I highly suggest you to read the blog post by Frank Dellert. And also there's a really nice GitHub repo by Jens Helene that just collects all the NERF papers. So there are probably a few dozens by now.
By the time the podcast is out, there'll probably be even more.
Yeah, that's true. So all these NERF papers assume that the scene is static at the time when we started the project. And the question is, how can you do NERF for videos? Because the geometry changes, so the branch of the network that predicts the density at each location kind of has to change if you want to have dynamic geometry. And then you could think of, is there a way to represent the dynamics of a face in a very low dimensional way, such that you can condition this network on the state of the dynamics, and then it predicts the correct densities. So this is where we employ 3D morphable models of faces. So this is a way to represent facial dynamics in a very low dimensional manner. So basically you have a vector of facial expressions that each one, it's you can think of it like a slider, and each one controls the vertices of a face mesh. So you can like make the person smile or make the eyebrow raised and stuff like that. Some of these morphable models are created using PCA analysis on the vertices of a template mesh that's warped to a talking person. Some of them are more handcrafted, but basically in the end you have a vector of 68 dimensions that just controls the entire geometry of the face. Now, obviously that's not accurate, right? Even if you track a face, you track a template mesh and you warp it to fit the subject, it's never really accurate. And that's why some of these facial reenactments don't look good, because they just use these morphable models and like change the texture or something like that. But the idea here is that all we need is this vector of expressions per frame. And we take this vector and we give it as input to our NERF. And then the NERF kind of can change the geometry. Now, this poses a few challenges because, first of all, while NerF is assumes like many different cameras around the scene, we only have one. Just assume a webcam that's in front of the person, like you and I are talking now. And this kind of pushes you off the NerF setting because you don't have multiple cameras anymore. But we overcome that by tracking the face and saying that it's the face that's static in a canonical space. The face is never actually moving rigidly. Every movement of the face is just movement of the camera, just by using the inverse matrix of the tracking. So then that puts us back in the NerF setting. So you have multiple cameras and just a face that's always in the same place. The only thing that changes is kind of small deformations in the face, like smiles, blinking, and things like that. And that is parameterized by the expression vector.
Okay, so let's for a second zoom out, right? You take as input a sequence of monocular RGB.
Exactly. I take as input a 2-minute video of a person talking. And my output is a representation of the scene, which is in the form of a radiance field, which is this ability to predict per point in the scene the color and density. And in the end, you are able to render this by providing for each frame, by providing the head pose and the expression vector, you're able to render a frame of the person with that expression.
Okay, so putting it into my own words, right? Your input is a 2-minute video, right? Taken from a static camera of a person's head. And basically, your output is this representation, which you usually use in order to generate new frames from. So you use to generate new frames that have new expressions and new poses of the head.
Exactly. Mm-hmm. Yeah.
So in the related work section, you basically, I'm assuming the best paper to look into before you read your paper would be NerF paper, right?
Yeah, that's true. In order to read our paper, it's pretty essential to know what NerF is and how NerF works. We don't change much upon NerF. We do just add another input, which is the facial expressions, and we still use the same network structure and the same losses. Mm-hmm. One more paper that you could read is some other facial reenactment papers that also use the morphable models. Deep video portraits is a good place to start. They also track a 3D morphable model and condition on expressions that they want to see, but they just use a CNN that does it in 2D.
Okay, so let's talk about the approach. So you get your video sequence, and what do you do with it?
So first we put the video through a face tracker. The face tracker basically gives us 6 degrees of freedom matrix of the pose of the tracked face mesh onto the frame. And as I said earlier, we use that as basically the camera positions for the NerF to train on, because we want the head to remain in canonical space. So we assume the head never moves, and the only movement is that of the camera. So we treat the output of the face tracker as the camera positions. This kind of replaces the structure for motion you would do in standard NerF training. In addition to that, we also get an expression vector for each frame from the face tracker. For each frame, we save these expression vectors, and we use them to condition the NerF. And as the NerF sees the different expression vectors, it is able to change the output density at each point in space, such that eventually the geometry deforms appropriately. There is one caveat that I should mention, that we also assume that we have a clean image of the background without the person in front of the camera. And the reason why we need this is because when you do this transformation into canonical space and you say, okay, the head is never moving, it's just the camera, but the video is actually a video of the person in front of a static camera, then it messes up the background basically. Because what you're doing, this transformation is true for the face, but it isn't true for anything that's not tracked. So you have to basically reintegrate the static background into the generated frames. So to do that, we assume a clean image of the background. And then in the volumetric rendering, we let the nerve basically assume that at the end of the rays, it just has the background. So we kind of inject the RGB of the background into the end of each rendering ray. So it implicitly learns how to incorporate the background. You could say it kind of solves alpha matting. Also, you get that for free.
Mm-hmm. Yeah. So I remember when I read this part of the paper, I was thinking, well, if you try to do a novel view, then there's the whole part of the background behind the person that is completely occluded, that you don't know how it looks like. So that's basically your way of integrating that information, right? You get an image of the background as well.
Exactly. That's basically the difference between novel view synthesis and novel post synthesis. That's why we cannot claim novel view synthesis, because you don't really generate the background from different views.
Mm-hmm.
Maybe I would mention that there is another very cool paper from the Google guys called NerFACE. There they actually do structure from motion and reconstruct the background as well. So they do novel view synthesis, but they assume they kind of take in the dynamics in order to factor them out, while our paper factors dynamics in order to generate new dynamics.
Mm-hmm. So I think we can move on to the results section. So this is a very interesting field, but I mean, I guess most people would ask you is how do you even evaluate this? So what are the common metrics that you use to evaluate?
Yeah, that's a great question, which is also very tricky for us, because I think it's very hard to evaluate. I mean, you have a video of a person, and now you want to generate him doing other facial expressions which you haven't observed, and that's super hard because you have no metric for that. So one thing that you can do is basically have a holdout section of the video, and then with your tracker you see what expressions he's doing, and you try to basically self-reenact the person. So that's one way how we tested our system, which worked pretty well. So on self-reenactment, which means holdout video, just try to use the video of the same person as a driving video for himself, for his own avatar, and this way we have ground truth. So we do that and compare to first order motion models, which is another paper that does zero shot reenactment of people. Basically, they train on a huge data set of people, and they learn to warp the image in order to reenact the face. And we compare to deep video portraits, which is the paper I mentioned earlier. They also track the face. They fit a 3D morphable model, but they do the image synthesis in 2D, whereas we do 3D and volume rendering. Each method has its own artifacts, I would say, but eventually ours, I think, looks better, more compelling. Deep video portraits has some artifacts when you turn the head, and first order motion model, as it's basically zero shot, it's not trained on the person, it obviously doesn't really preserve the identity pretty well. And this also shows in the numbers. So what we use is just the traditional image reconstruction metrics for this setting. So you have L1, PSNR, LPIPS. PSNR is a peak signal to noise ratio, which is measured in decibels, but it's pretty much correlated with L2. We use SSIM, which stands for Structural Similarity Index Measure. It's also used as a metric for image reconstruction. It takes into account local details, also contrast, sharpness, stuff like that. And finally, we also use LPIPS, which is the Learned Perceptual Similarity Metric, that basically passes both images through a pre-trained neural network and kind of outputs a measure of how a human would prefer, or how a human would rate the similarity between these images. From my experience of training these, LPIPS is a really good metric. And we also perform really well on this metric if you compare to the other methods. So each metric, I would say, suffers from different sensitivities. For example, when you take L1 or L2, if everything you generated looks really good, but it's just a little bit translated in pixels, then these losses won't give you a good value. LPIPS, for example, is a little bit less sensitive to that and just takes, from my experience, general perceptual quality into account. So yeah, I kind of like this loss. And it really correlated well with how good the images we were generating.
In order to truly understand its impact and performance, you actually need to see the results. So I'm going to put a link in the description to the project website where the listeners can actually go in and view the actual results, the videos. They do look really well. Okay, anything else you want to add on the results section?
So we show, I talked about the self reenactment, and that's how these are mainly our qualitative and quantitative results, but we also did show some just free control over the pose and the expression, which is not something you can measure, but it's I think it's also pretty important when you read such a paper and you see with your own eyes how well it does. So we do stuff like freezing the expression and changing the head pose. And in the video that accompanies the paper, you can also see cross-subject reenactment. So you see one person moving his head and saying something, and then you'll see another person that we trained on doing the same thing. And what's cool here is that we don't have to train on the pair. So if you think about deep fakes, for example, that just fit a latent space to fit these two subjects. In our case, all you have to do is train on the person you want to generate. And the driving sequence can be anything. You just have to use the face tracker to get the head pose and the expressions.
Okay, so
Yeah.
it's easy to move between people in that sense.
Yeah, between driving people. For the actual person you want to see on the screen, you have to retrain. It's still quite far away from, at this point, what we did was far away from running real time, which is probably what everyone would like to have. NerF, as it does volumetric rendering, you have to sample many points along the rays, and you have many rays if you want to get high resolution output. So it just means so many calls to your MLP, and it's a little bit slow. So for 512 pixels, it would take something like 9 seconds to generate a frame on a single GPU. But yeah, I mean, today you can already see new papers coming up every other day that do NerF really fast. So I think there's a lot to come in this direction.
Yeah. What about like fail cases? When do you guys fail?
So the main thing that I'm not happy with personally is that we only track the face, and the face does not always move the same way as the torso and the neck do. And since we use this canonical space, then you could sometimes, so like you cannot simulate just the head moving and the neck staying static with our system, because they move together basically. And we would like to incorporate tracking for the torso and the neck. So you could treat it as a failure method, but because you would get like the torso moving with the head. And of course, for like very extreme head rotations that you never trained on, the network would not know what it should render in the end. So you might get some artifacts there. But I think the NerF artifacts are not as bad as GAN artifacts would be.
Mm-hmm. Yeah, actually, when I was reading the paper and I was looking at the images, I noticed something a little bit, I want to say, funky about the eyes. Right? There's something about the eyes. Can you comment on that? Why do the eyes look a bit? Not sure what the word for it, right? But so there's some issue with the eyes. They like
So the eyes is also something we weren't using the tracking of. You could say the eyes are like the torso basically. So the eyes, any movement you see in the eyes is just coming from correlation that the network has picked up from. So maybe in the video when someone like turns his head to the right, then the eyes usually look to the left, because that's human nature to always look at the camera. So I think the network picks up on that and tries to like move the eyes when you do an extreme head pose. But yeah, anything that's not tracked is more susceptible to looking weird or unnatural, I would say. But I think it's totally possible to incorporate eye tracking. It's also, you can parameterize it in a low dimensional way and use it just as we use the facial expressions. We just didn't do that.
Let's talk a little bit about the conclusion and future work. So like, how do you see the impact of this paper on the field? And if any new PhD students are listening to this, what do you think is a good next project? What do you think should come next, without revealing any internal lab secrets?
Yeah, so the first thing is this paper kind of validates that NerF can be used for dynamic scenes as well. And I have to say, like, we uploaded our paper and pretty much in the same week you had like 4 or 5 more dynamic NerF papers. So we weren't the only people who were thinking that NerF could be used for videos. And the other papers also do a great job. But ours did show that it can be used for synthesis of novel dynamics, because most of the other papers were just doing replaying of the videos just from other viewpoints. So that's something our paper validates. It also validates that 3D morphable models could be used for NerFs. They're good conditioners for NerFs. So regarding future work, there's already a paper that appeared online called AD NerF, and they kind of build up upon our paper, but they also add torso tracking. So they, in a way, they solve one of the problems we had, and they combine it with deep speech. So they animate the person using audio input. So this is very similar to the neural puppetry paper from Justus, Thies from our lab, who does the same thing. He uses the deep speech features to animate a 3D morphable model and then generate a frame of the person that looks photorealistic. So they just do that combined with our paper. I think that's really nice. And of course, what would be really nice to see is doing human bodies in general. These 3D morphable models exist not only for faces, but also for whole body. So you have the most important one is probably SMPL from Max Planck, and would be really cool to see someone doing something with that.
Okay, so now for my favorite part of the podcast, what did reviewer 2 say? So what comments did the reviewer had in the review process that made the paper better?
Yeah, I think we were pretty lucky here. We actually didn't have reviewer 2. We only had reviewers 1, 3, and 4. Yeah, in general, they all they were pretty happy with the results, with the quality of the images that we were generating. They also liked the simplicity of the idea of just conditioning NerF on a 3D morphable model. They did want to see some extra sequences. So one of them wanted to see what happens in video when we freeze each of the inputs every time to the radiance field and see the effect of it. Since we do have this background separation and integration, one of the reviewers asked for a sequence where we have a person with a kind of more elaborate background, because some of the backgrounds we were using in the initial data set were kind of simple. It was just a wall. So we had to re-record that. And also they asked for audio in the videos. In the initial data set, we didn't have the audio of the people talking. We just had the video. So I had to create a new data set where people actually talk, and it's nice to see how the lip sync works when you regenerate a video and you can have the audio of one person speaking one language and then you transfer it onto another person. So this will be up in my second supplemental video that I'm going to upload to the project page. You can see that how the reenactment works with audio. As for the reviews, I can say 2 reviewers gave weak accept and 1 gave strong accept.
Okay, so that was it for dynamic neural radiance fields for monocular 4D facial avatar reconstruction. Thank you very much, Guy, for being a part of this podcast. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.